Is it okay now? Yeah, now it's okay. Thank you very much, Michal, for your welcome words and sharing your thoughts. Now we are going to start with the series of keynote presentations. And first, we will receive first-hand information on the next evolution of sustainable building technologies. And I have now the big pleasure to announce Dr. Peter Richner from EMPA. The floor is yours.
Yeah, good morning, everybody. Thank you once more for the invitation to be here. I must say, I seldom had such good introductions as from Michael and Fabrice. If I compare that, what I hear in Switzerland from politicians, I think it would be easy for you to have a splendid career. and we desperately need people like that. So, how to make building stock part of a sustainable future. This is what I would like to talk about. And we know we struggle with many things. Fabrice mentioned that Switzerland is always on top when it comes to innovation. I would debate that to some degree when it comes to the construction sector, and I will explain you why. So, but let's see, what are the main challenges we are facing? In Switzerland, this is the final energy use, as it is at the moment. About 2/3 is fossil, and we have about 10% nuclear, electricity, and some biomass, and so on. And we took a couple of political decisions in the past. In 2017, we passed a law which said that we are going to operate the existing nuclear power plants as long as they can be operated safely, but we're not going to build new ones. And we have agreed to the Paris Agreement, to this net zero target. Just a couple of weeks ago, we had a vote where we said, okay, really by 2050, we will be by net zero. So from this, what we have here, all of this is going to disappear. We need a new solution for about 70% of our final energy demand. And that's not a piece of cake, huh? To be honest. And the question is, okay, if we look back, we talk about those things for a long time, or are we on track? Here you see the final energy since 1990. So in 1990, 81% was nuclear and fossil, and by 2020, we went down to 68%. So in 30 years, we reduced it by 13%. Now we have another 30 years to get rid of the other 68. So more of the same is certainly not going to do the job. And we know we are too slow. We have to accelerate, definitely. And then we have to see, okay, what do we need our energy for? And in Switzerland, it's about 45% is for buildings, 30% for mobility, and then industry and so on. And I think in order to develop a strategy, one has to understand also how energy and climate are related. And there is a very simple equation developed by Kaya. Kaya is a Japanese economist who has contributed to the first ICP reports. And he said the CO2 emissions are basically composed of how much CO2 per energy unit you emit. This is basically how much fossil energy you have in your system, times how much energy you need to create the good. So here, energy per GDP. This has to do, of course, with efficiency, basically, times, well, how wealthy you are, you know, how much GDP you produce per capita, times capita. So you see, it's very simple. Huh? Everything goes away and CO2 equals CO2. But using those 4 factors is quite interesting to analyze what's going on. And we have here 2 technology-driven factors, the fossil part of the energy system and the efficiency. And we have 2 socioeconomic factors, which are about economic growth and growth of population. And what is also clear from this equation, if you want to get to net zero, at least one of the 4 factors has to become zero. This is also not difficult. Now we can start argue about which of the 4. But now let's switch to buildings. And I'm going to replace the GDP by square meters of heated area. This is, I would say, the proxy in this equation if we talk about buildings. How many square meters you have? So I did an analysis in Switzerland for the heating demand of private households, and then you can see, again starting at 1990, if we look at CO2 per energy, well, for about 15 years, nothing happened at all. And then we started slowly to decarbonize, and now we are at about 80% that we use or emit CO2 per square meter. Efficiency-wise, energy per square meter, we are down to 63%. So already in 1990, we had efficiency measures, and we kept on working on that, and it went down and down. If we look at the two socioeconomic factors, we see the square meter per capita went up by 7%, which is, it's less than most people think. But, and that's the most important part in Switzerland, we had for 30 years, we had 1% population growth. And of course, that adds in this equation. Okay, so now, here I have the technology factor, so energy or CO2 per energy times energy per square meters, and then here I have the socioeconomic factors. This is where we were in 1990. Initially, we had to go by 2020 to reduce it for buildings by 40%. So we have to come to this curve somehow. At the moment, we would like to go down by 65% by 2030. And now look, let's see what happens. So in 2000, we were there, 2005, 2010, 2015, 2020. So we did not make it. We did not hit the red curve. But what we can say on this technology axis, we improved by 50%, which is quite an achievement. But at the same time, on the socioeconomic axis, we went up by 38%. So as a result, we only reduced the emissions by 31%. That's the way it is. Of course, coming from a material science institute, I feel mostly responsible for the technology axis. But we should not forget about this one. We cannot, and this is sustainability. Sustainability is economy, social, and environment. You have to work in all directions. Now, if you look at the buildings in Switzerland, residential use by construction year, we see that 70% of the building stock has been built before 1990. And this is before we really started to improve the energy efficiency of buildings. And so we were thinking about, okay, how can we address this huge stock of buildings? For example, we have plenty of those relatively small multifamily homes which are terrible in terms of energy, which have to be renovated also internally and so on. So we said, okay, we want to develop this retrofit technology. We want to look what are geometric characteristics, get the geometry outside, because we wanted to work with prefabricated facade elements. And actually, a facade is not really a plane. You will see. So we took drones, did then measurements of the geometry of those buildings, including the roofs, etc. And everybody had then access to those data. We built a digital model of those buildings. And based on that, we said, okay, we are going to do everything from the outside. We have a facade element which just attaches to existing building. It's prefabricated. It brings the new window with it. Also, heating, cooling, everything comes through the facade so that the internal work is really limited. You don't have to do too much internally. You just can stick that together like Lego and then do that for all the openings, insulation. We developed also a system for the roofs and so on. And we did it also in reality. It was not just a research project. We did it on houses, and we converted this building into this. Still the same building. And we saved around 80 to 90% of the operational energy. And still it is an economic case you can make, because we replaced this roof by an additional flat. And this is the most expensive anyway in this building, and that's going to pay for the whole renovation. So, very nice project. And then there is an Association for Energy Efficiency of Swiss Industry, and they had their first national congress on heating, May 23, and they used this picture on the flyer, and of course I was pleased to see that. I was there also invited to give a talk. But So this was this spring. Huh? We did the research project 2005 to 2008, and the building was renovated in 2009. And now 15 years later, they say, look, how wonderful. So the question is, even though we have a very lively and I think also good research community in Switzerland, we completely fail when it comes to technology transfer. We are not there where we should be. It cannot be that we develop something and 15 years later, this will still be used as an example of how to do things. This is completely ridiculous. Okay, so we developed this nest concept where we said, okay, we want to have a living lab where we can scale up things, including real users. But it should still be research dominated, so that also means we can take risks. If you build something like that, you do not want to take risks. It has to work on day one. Okay, this also means that the users who are in this building, sometimes they have to suffer a little bit, but that's okay. It's a public-private partnership, so in all projects we have a very close collaboration between people from academia and from industry with the goal to take something from the lab and scale it up to the point where industry can bring it to the market. It's holistic, so we can look at all kinds of aspects, and it's also dynamic, so we wanted to have a maximum of flexibility. So how does this thing look like? Well, that's how we started. This is what we call the backbone of Nest. It's a core with freestanding platforms. And on those platforms, we can build small buildings. We call them units. And each of those units is developed by a consortia from industry and academia and addressing a specific topic. So that can be an office, it can be an apartment. We even have a solar fitness and wellness unit. We build them, operate them. And once we learned what we can learn, we can take them away again and can build something like that. So it's the absolute dream of every constructor because it's a construction site which never stops. This is what it looked like a couple of years ago. And of course, what is essential, and that always comes first, buildings are here for people and not the other way around. So you have to deliver quality of life and comfort, and it has to work. So that we always addressed. So we really also designed very nice rooms, even though, for example, here it's about design for disassembly, but most people, they couldn't care less about circular economy. They want to have a nice apartment. So they get into this unit and first thing they say, it's nice. And then you tell them, and by the way, it's designed for disassembly. Okay, so what are we looking at? First of all, I think we have to operate our buildings in a much more intelligent way. So two of our employees developed a system where they can actually control the heating and cooling on a room in a much more precise way by putting just one sensor there and have access to the vent which is controlling heating and cooling. It takes you about 2 weeks of measuring some artificial intelligence and physical principles, then you include metadata, and then you can actually very precisely follow the set temperature curve that you want to have. They have now founded their own company. We did that. This is an office building of EMPA from the 60s. We installed it here. So all we did is we replaced this control part, and we added a sensor, and then we have a connection between the Danfoss system and Weibo, and we saved 20% of heating energy. Did not replace windows, did not do anything on the facade, just have a sensor and replace the control of the vent. That's all. And well, 20% is not so bad. And quality was still okay, and with the energy prices we have at the moment, return on the investment is only a couple of years. Okay, then I think we should make more use of what digital technologies can bring us. So this is a picture of when the main building of ETH in Zurich was built in 1919. And this is a picture of the Zurich Prime Tower 2009. And now this is like, you know, this game we played when we were children, find the 7 differences. Well, the first one, obviously, on the left, it's black and white. On the right, it's in color. On the right, they are wearing helmets. Okay, can you find something else? You see, it's already getting difficult, huh? 100 years later. So we, together with ETH, we developed this living unit. It's a 3-story living unit, apartment unit for 4 people, about digital fabrication, really implementing digital technologies starting from planning all the way to construction and operation. So for example, we had a robot on the construction side which was able to take reinforcement steel, cut it and weld it to get this double curved wall which has a very special shape and which is actually taking the load of the upper 2 floors. It's a very slender wall because it will not buckle due to the double curve. So you don't need as much material as you would normally use, but you can do this reinforcement not by hand. You cannot follow this digital form. For that, you need a robot. Then we did the casting still in a traditional way, and this is the way this wall now looks like. Another system are the floors. In floors today, we have a lot of concrete which has no static function. It's just there because we pour concrete into it. So here is a 3D sand printing system. We created the form, then we sprayed the concrete, and we only have concrete where it is needed from a static point of view, and you can actually reduce the mass by 50% or even more. You're also able to create very interesting forms, whether you like this shape or not. This is now another thing, but you can do whatever you want. Closed circles. Why is this important? Let's do an artificial calculation. In Switzerland, we have about 380 tons of construction materials per capita. So for each inhabitant in Switzerland, there are almost 400 tons of material. The population growth is about 2.6 persons per second. Let's assume that those 2.6 persons would like to have the same as everybody has in Switzerland. This means 990 tons per second, 59 million tons per minute, 3.6 billion tons per hour, or 85 billion tons of construction material per day. I mean, there is just no way we can do that. So what are we going to do? Well, option 1, we tell the 2.6 persons, sorry, you're too late. You don't get this. This is more or less what we do today. Or we find another way. And one thing which can add, of course, is not do something like that. Today, we just tear down buildings. We are not able to deconstruct them. And this is because they have not been designed and built with the aim to reuse things. So we did this urban mining unit with Werner Sobeck from Stuttgart and ILEC, University of Stuttgart and Karlsruhe Institute of Technology. And the basic idea is that we say a building is borrowing materials for a certain while from circles. And after this use, it gives it back either to the biological cycle or to the technical cycle. We talk about modularization, prefabrication. All the materials and products we use can be removed and can be reused. It's a residential unit we opened some years ago. This also means there is nothing is glued, there is no welding. Everything is just put together by mechanical connections. We always say 2 people with a screwdriver can take apart the whole thing completely. Again, this is what it looks like. You see, of course, a lot of timber, but also other materials, and this is the explosion drawing of this whole unit. It was prefabricated. You can see here when the modules were delivered to Nest. That was done by the Kaufmann-Zimmerei in Austria. On day 1, we installed 124 square meters of prefabricated living space. Second day, we closed the envelope, and then in the following days, there was a little bit of interior finishing. So you also see if you go really consequently for prefabrication, you reduce the construction time on site enormously. And this is also about money. And also, prefabrication normally gives you much better quality because people fabricate this in a controlled environment, not outside at -2 degrees, snow or whatever. No, it's a production hall where you have all the equipment you need. Again, this is one of the pictures from the inside. We also reuse sometimes components like those doorknobs. They come actually from a bank which has been torn down, but something like that will never be destroyed. You can use that forever, and it's a nice piece of design. So reuse it. But then there are also other materials, like this is recycled glass, foamed, which is then from an acoustic point of view very interesting. Or this drywall here, those are Tetra Pak flakes. You just press them together. They have enough organic material that they stick together, and you can produce a wall out of that. Works perfectly. Okay, and then, of course, the operation has to be CO2 free. So what we have, we connected all the units to different energy systems. We have 3 heating systems, so we can actually pump heat from one unit to the other. We have seasonal storage units that we can store heat from the summer into the winter and then bring it back. We have a lot of PV everywhere. We store that in batteries for short term. And for longer, short term means a day or 2 or maybe 3 days. For longer days, we have an additional demonstrator which is made for mobility mainly. And here we have an electrolyzer, so we convert electricity into hydrogen, which makes it much easier to store. And this hydrogen can then go to mobility, or we take it back to Nest and convert it to electricity and to heat with, now I forgot the word. No, the heat pump is the last part. Anyway. We also operate this unit as a completely open research platform. So researchers from even all over the world have access. We have all the data, like live data, from this week, weather forecast, how much solar energy we produced, what is in the room. We have about 2,000 measuring points in Nest that we measure every 5 seconds. And for example, people at EPF in Lausanne, they develop new control algorithms. We can give them access to one single unit or to the whole of Nest, and then they can operate the whole thing from remotely. Important here, we do not optimize one single unit, but the whole ensemble. It's clear if you're on the roof, you can collect much more renewable energy than if you're on the first floor on the northeast side. So they have to help each other. But maybe the one on the northeast side has more mass and can use that for storage and so on. So presently we have around 150 partners from industry and the public sector. And the question, of course, is, okay, does it now really help to accelerate innovation? We see a lot of products which are now on the market, which have started at Nest as prototypes. We also did one unit together with Barbara Buser, who is going to talk afterwards about circular economy. Also, a lot of concepts have been taken over and people try really to implement it. But honestly, we still have to get much faster. And what I showed you is, of course, from the Swiss perspective, it's determined by our boundary conditions. Your boundary conditions here in Poland are certainly somewhat different, but still I hope that you can use some of the things that I have shown for your own, because we have to look at those things and we have to explore the future of buildings, because, as you said, they are one of the most important parts of our society. We typically spend 80 to 90% of our time in buildings, and if you're not in a building, you're typically on a transport infrastructure which is connecting one building to the other. So the built environment is absolutely key for our quality of life, but we know we have to make a big step to make it sustainable, and I hope we all together can contribute so that we will reach this goal. Thank you very much for your attention.